Welcome back to G Fun Facts Online. Today we are traveling to the southern hemisphere, specifically to a windswept ridge on the Chilean Andes known as Cerro Pachón. It is late 2025. The air up here is incredibly thin and dry, offering a view of a pristine, ink-black sky that has drawn astronomers to this region for decades. But tonight, we are not talking about just another telescope. We are talking about the awakening of a machine that has been called the Great Eye. This is the story of the Vera C Rubin Observatory, and, more specifically, the technological beast beating at its heart, the LSST Camera. This instrument is a record breaker in every sense of the word. With a resolution of 3,200 megapixels, that is 3.2 gigapixels, it is the largest digital camera ever constructed for the field of astronomy. To give you a mental image, this camera is roughly the size of a small car, or a compacted SUV, and it weighs 3 tons. For the next 10 years, this machine is going to scan the entire visible southern sky every few nights, not just taking photos, but creating a color motion picture of the universe. So let's skip the long introductions and get right into the engineering. Because to understand why this matters, you have to understand the sheer physical reality of this device. In an age where the camera in your pocket is measured in millimeters and grams, the LSST camera is a leviathan. It is a cylinder about 5.5 feet by 10 feet. It is not just an attachment you screw onto a lens. It is an integrated physics experiment all on its own. It houses a utility trunk, a cryostat, a shutter, and a filter exchange system. At the very front of this assembly sits the largest high-performance optical lens ever fabricated. They call it the L1 lens. It is 5.1 feet in diameter. The precision here is mind-boggling. This glass was ground and polished to such an extreme standard that if you were to expand this lens to be the size of the continental United States, the highest mountains and deepest valleys on its surface would be less than an inch tall. Behind that massive front element sits a second lens, and then a third, which acts as a vacuum window for the sensor array. Now, let's talk about the retina of this great eye. This is the focal plane, and it is a technological masterpiece. It is a circular array, about 25 inches across. But it is not one single sensor. It is a mosaic composed of 189 individual charge-coupled devices, or CCDs. These sensors are grouped into 21 square units called rafts, each containing 9 sensors and its own dedicated electronics. Each one of these rafts is a self-contained unit worth up to $3 million. The engineering challenge here was alignment. To get a sharp image, the flatness of this focal plane is critical. These sensors had to be aligned to within 10 microns, that is 1/10 the width of a human hair. The result is a 200 megapixel resolution. To display a single full-resolution image from this camera, you would need nearly 404K ultra-high-definition television screens arranged in a grid. A single image covers a patch of sky, roughly 40 times the area of the full moon. The detail is so fine that a golf ball visible from 15 miles away would appear distinct and sharp to this camera. But electronics generate heat, and heat creates noise in digital images, that grainy static that ruins low-light photos. In astronomy, that static can obscure faint stars or distant galaxies. To combat this, the focal plane is housed inside a vacuum cryostat. The sensors are deep frozen to approximately -100 degrees Celsius, or -148 degrees Fahrenheit. This renders them incredibly sensitive, allowing them to detect individual photons of light that have traveled for billions of years. The Rubin Observatory is a survey telescope, which means speed is everything. It takes a 15-second exposure, reads out the data in 2 seconds, and moves to the next patch of sky. This requires a mechanical shutter that is both massive and incredibly fast, opening and closing thousands of times a night. It also uses 6 different color filters to analyze the physics of the objects it sees. These filters are huge glass discs, each weighing nearly 90 pounds. An automated mechanism inside the camera can swap these massive filters in less than 2 minutes. Imagine a mechanical ballet performed in the pitch dark, at the top of a mountain, potentially in high winds. That is the daily reality of the Rubin Observatory. Now, if the hardware is the body, the data is the lifeblood. The Rubin Observatory is often described as a big data project that just happens to do astronomy. The volume of information is staggering. Every night, the camera captures about 1,000 images, generating approximately 20 terabytes of data per night. Over its 10-year survey, it will amass 60 petabytes of raw data. That is equivalent to over 10,000 years of high-definition video. The journey of that data is a race against time. As soon as the shutter closes, the data is sent via fiber optic cables down the mountain to the base facility in La Serena, Chile. From there, it jumps over high-speed networks to the U.S. data facility at SLAC National Accelerator Laboratory in California, as well as mirror sites in France and the UK. But here is the most ambitious part, the 60-second alert system. The universe is dynamic. Stars explode. asteroids zip by, and black holes flare. If astronomers wait weeks to process the data, they miss these fleeting events. So, Rubin's software pipeline compares every new image with a template of that same spot from a previous night. Any difference? A new point of light, a brightening star, a moving rock, triggers an alert. The goal is to issue a public alert to the world within 60 seconds of the shutter closing. They estimate Rubin will generate up to 10 million alerts per night. Since no human can read that many, automated software brokers will sift through the stream, notifying other telescopes to follow up. So what are we looking for with all this power? The scientific mission rests on 4 main pillars. The first pillar is the dark sector. Ordinary matter, the stuff we, the Earth, and the stars are made of, only makes up about 5% of the cosmos. The rest is dark matter and dark energy. We know they exist, but we do not know what they are. Rubin is designed to find out. By detecting millions of Type Ia supernovae, which act as standard candles of brightness, Rubin will map the expansion history of the universe to understand dark energy. It will also use a technique called weak gravitational lensing. Dark matter is invisible, but its mass bends light. By measuring the subtle distortion in the shapes of billions of galaxies, Rubin will map the clumpiness of dark matter over cosmic time. The second pillar brings us closer to home, the inventory of the solar system. Rubin acts as a sentry. One of its congressional mandates is to catalog potentially hazardous asteroids, rocks larger than 140 meters that come close to Earth. These objects are dark and fast, but Rubin's frequent imaging will allow it to link the moving dots. It is estimated that Rubin will increase the number of known asteroids from roughly 1 million to 5 or 6 million in just 10 years, cataloging up to 90% of potentially hazardous asteroids. It is also hunting for the elusive Planet 9, a hypothetical massive planet far beyond Pluto, and scanning for interstellar objects passing through our system, like the famous Oumuamua. The third pillar is the transient and variable sky. As I mentioned, the static night sky is an illusion. The universe is a fireworks display. Rubin will discover millions of supernovae and hunt for kilonovae, the collisions of neutron stars that create gold and platinum. It will also watch stars wandering too close to supermassive black holes, getting torn apart in tidal disruption events. It will provide light curves, or graphs of brightness over time, for billions of stars, revealing their dynamic lives. The fourth pillar is mapping the Milky Way. We live inside a spiral galaxy, which makes it hard to see its structure because of dust. Rubin's infrared capabilities allow it to peer through that dust to map the position and motion of billions of stars. It will look for stellar streams, groups of stars moving together that are actually the corpses of smaller dwarf galaxies our Milky Way cannibalized billions of years ago. This is galactic archaeology, reconstructing the violent history of our galaxy's growth. Getting to this point was a marathon. The camera was built at SLAC in California. The assembly in the clean room was a high-stakes operation. Engineers described inserting the sensor rafts into the grid as parking a Ferrari in a bedroom with 0.5 millimeter of clearance on each side. Then came the transport in May 2024. Moving a 3-ton priceless instrument to a mountain peak in Chile involved a chartered cargo 747 and a careful truck ride up winding dirt roads where every bump was monitored. Now, fully installed, the Rubin Observatory is doing something radical with its data. Historically, astronomers got dibs on their data for a year or two. Rubin shatters this. The data becomes available to the scientific community immediately. And it is not just for professionals. Through citizen science portals like Zooniverse, the public will be invited to help classify galaxies or spot asteroid tracks. A school teacher or a student could be the first person to discover a new supernova. Education interfaces are being built so classrooms can adopt a patch of sky and monitor it throughout the school year. As we stand at the end of 2025, the 3.2-gigapixel eye is open. The dome rotates silently. The shutter snaps open for 15 seconds, then closes. Read out. Move. Open. For the next 10 years, this rhythm will build the most comprehensive record of our universe ever attempted. We know we are looking for dark energy and killer asteroids, but the true promise of Rubin lies in the unknown unknowns. With an eye this sharp and a memory this deep, we are bound to discover things we never even imagined existed. The movie of the universe has begun, and thanks to the Rubin Observatory, we are all watching. Thanks for listening to G Fun Facts Online.